So today's problem, and by the way, these are things that you should have all the tools to solve. So, all right, so today's problem. Let f of x equal ax squared plus bx. Okay, so it's some unspecified quadratic. It does not tell us what a and b are. Given that the average rate of change of f of x over the interval 0 to 2 is 1, and I should point out this notation here, square bracket 0, comma 2 square bracket means x equals 0 to x equals 2. Okay, and the average rate of change of f of x over the interval from 1 to 3 is negative 3, then what is the value for b? Did anybody get an answer for this that they're brave enough to say? You have a 1 out of 5 chance, of course. And the answer is C. B should be 5. How do we do it? We translate. So we say, okay, the average rate of change of f of x over the interval 0 to 2 is 1. Says, write down the average rate of change formula is 1. Well, that says f of 2 minus f of 0 is 2. But we can plug 2 and 0 into our function. And that gives us 4a plus 2b equals 2, or 2a plus b equals 1. So we get a relationship between a and b. Repeat. We have the average rate of change over the other interval is negative 3. So we have the average rate of change from 1 to 3 is negative 3. Again, clear the fraction, plug in to our function, simplify to get a relationship. 2 equations, 2 unknown, our bread and butter. And so if we say subtract the first equation from the second equation, we get a is negative 2. Plug that back into the first equation, we get b equals 5. And we have our answer. Good times were had by all. All right. On to today's thought. Our thought for today. And this is a quote from the great philosopher Jake the dog. You might know his work with Finn the human. So Jake the dog had this to say: sucking at something is the first step towards being sort of good at something. And so it's okay to be bad when you start. Almost everybody is. And I would say really everybody is, but some people are willing to admit it. You get better. You get better. So it's okay. Don't get discouraged. Keep going. Keep going. Okay. Now, where were we at? Last time we talked about this notion of an average rate of change. So we said, okay, if I have my function here, and let's suppose we plot a function, I can talk about the average rate of change from 2 points. So if I have my A, and then over here I can have my point B, then the average rate of change, we said, that's like the slope of the line. So the slope of our secant line, that's our average rate of change, I'll abbreviate AROC, that's f of b minus f of a over b minus a. However, we said, what we'd really like to do is not just say what's the average rate of change between 2 points, but what's going on? What's going on at A? And there was this idea, it's like, well, if you look really close, it looks flat. So in particular, there's this line over here, which is the tangent line. Now the word tangent comes from, I think it's Latin, but it means to touch. So it touches the curve. So the tangent line, and if we look at the slope, that's our instantaneous rate of change. And the hard part about this is it's a very long word to spell out, so it makes it, you have to do a pause. And now we say, well, that's what we're after. So how do we get it? Well, here's an idea. Well, we'll find the average rate of change from A to A. Right? Why not? Well, plug it in. What do you get? F of A minus F of A over A minus A, also known as 0 over 0. Okay, so that's our answer, right? Well, a small aside. What's wrong with 0 over 0? And in general, what's wrong with dividing by 0? So we say that A divided by B is equal to C if A equals B times C. So what do we mean by that? 6 divided by 2 is 3. Why? Because if you multiply 2 and 3 together, you get 6. All right, so let's take A and divide by 0 and say, let's call that answer C. Well, if we apply this idea, then that says A needs to be 0 times C. But 0 is magical, has this wonderful, beautiful property. It turns out, if you take 0 times anything, you get 0. So the conclusion is, if you have A over 0, if A is not 0, you're in an impossible situation, because this says A has to be 0. So that's why you can't divide. It's just impossible. It won't work if A is non-zero. But what happens if A is 0? Oh, something else happens. Now, it's not that it doesn't work, it's it works too well. What value of C is it true that 0 times C is 0? Anything. Or maybe nothing. So the problem is that 0 over 0 is ambiguous. We call that more work. More work. So whenever you see 0 over 0, our mantra is more work. It's ambiguous. We don't know what it is. Okay, so now we're like, nope, not going to happen. It needs more work. Okay, so we can't just plug in at that point A. So now, what happened? So this is a small history lesson. Newton had an idea. And Newton's idea was, well, I'm going to go infinitely close to A. That was his idea. I'm going to start at A, then move it so super tiny distance away. Infinitely small. You're like, do you mean 0? No. Not 0, but infinitely small. And, well, there's two things that happen. Now, as Newton had this idea and he tried it out, one pro to this is he got the right answers. You know, that's why we still talk about him hundreds of years later. But there's a small con, which is, it's just a bogus approach. You can't be infinitely small and be non-zero. And mathematicians were really perturbed by him. Mostly because he got the right answer, even though it was unjustifiable. Okay, so that's not going to work. On a side note, you could make it work, but it would take about another 3 or 4 years, so we're not going to go that way. So one other way to think about it is Newton said, I'm going to come up with this weird number, and that's going to work. So mathematicians kept thinking about it, and they said, okay, so instead of trying to come up with a number, a single number, in an infinitely small number, we're going to think of a process that goes to 0. So in other words, we're going to have a way to look at things as we get smaller and smaller. So if you remember at the end of the last lecture, we said, okay, we're going to zoom in. We're going to get closer and closer. And this was the idea of what is known as limits. And so we are going to now do a detour on our discussion. So if we think about the grand picture of where we're going for calculus, we're trying to understand rates of change, which means we're after the slope of the tangent lines. And to get to the slope of the tangent lines, we need to understand this processing. How do we go to 0? Now, that's, let's see, what do I want to say here? Well, okay, I'll say the following. So the idea here is we write this as the limit as x approaches a of f of x equals L. And I'll write this out in longhand. The limit as x approaches a of f of x, and then of course we have our equals is, and L. So the intuition is the following. It's saying what's happening to f of x as we get closer to a. In other words, what's happening to an expression? Now, the big takeaway is what are limits about? Remember how I said 0 over 0 is ambiguous? It means more work. The moral is, this was not a well-planned page. Limits tell us what should happen. So in other words, it helps us resolve the ambiguity. They don't tell us what does happen. They tell us what should happen. And so they do it by looking at things nearby. Now, I have some good news for you. Let me pause for a second. Any questions? We're going to go into details in a second, but any questions? Okay. I have some good news for you. Some of you may have had to go into this type of discussion, which is the technical definition of limits, which says, well, what does it mean to say that the limit as x approaches a if f of x is L? So the technical definition is the following. It says for all epsilon greater than 0, there's a delta greater than 0, so that if 0 less than x minus a less than delta, an absolute value, then absolute value f of x minus L is less than epsilon. The good news is, this is the end of our discussion about the technical definition. So you don't have to worry about epsilons and deltas. We're going to go off of intuition. But there is some underlying things. And by the way, in case you are wondering, how does this fit in with what we talked about? What we're really saying here, when we talk about limits, we're saying that as x gets close to a, f of x gets close to L. So when you see these absolute values, whenever you see absolute values, that's a measurement of distance. So in particular, when we're talking about the absolute value of f of x minus L, we're just saying that the amount of difference between f of x and L is very small. That's why we say epsilon is very small. And we can say, I can guarantee it's small as long as x is sufficiently close. So really, this is just saying x is close to a and f of x is close to L. All right, so that's the end of our discussion about limits, at least as the technical part. So let's test some intuition here, a little bit of intuition. Given that the limit as x goes to 0 of f of x equals 4, so as x is getting close to 0, the function f of x is getting close to 4. That's how we think of this statement. When x is near 0, f of x is near 4. And the limit as x approaches 2 of f of x is 0. So again, as x is close to 2, the function f of x is close to 0. What can we conclude about the limit as x approaches 1 of f of x? So what's happening at 1? All right, so there's 4 options here, A, B, C, D. The first option, the limit goes to 2. The second option, the limit converges. And converges is just a way of saying there's an answer. There's a number. But we don't know what that number might be. The third option is that the limit doesn't converge. So it's possible that there's no way for it to work. We'll see examples of that in a second. And the fourth option is none of the above. All right, so take 15, 30 seconds. Ask your neighbor, what do you think is true? What do you think is true?
D because of things like piecewise functions that break apart at certain points?
Yeah, so the answer is D. D is the answer. Now, why is it D? This is actually, there's a nice message here about why D is the answer. What's happening here is this part is telling us something about close to 0. This part is saying something about close to 2. And that's all the information we're given. Now, the question for you, is 1 close to 0 or close to 2? No. In math terms, in our setting, they're far apart. You might say, well, wait, it's just 1. But because we're in the continuum, this is a very fancy way of saying between 0 and 1, there's like infinitely many numbers. There's a huge gulf. And so the issue here is we only can make conclusions about things close to 0 and things close to 2. And 1 is far away. So in calculus, we oftentimes work on the nearby. We're saying, what's happening nearby? And so because 1 is not near 0, because there's a definite distance between them, we're not able to make any conclusions. So the answer is D. So, all right, that's okay. Don't worry. Now, after I just said that, I am going to make a claim that limits are intuitive in many cases. Okay, so let's start with some simple ideas. Let's suppose I'm asking, as x gets close to a fixed number c gets close to what? It gets close to c. Because what's happened to that fixed number? It's not changing. It's always c. It's like no matter how close x gets close, x is near a. No matter how close I am, c is still c. So you're like, oh, it should always be c. Life is good. All right. Now, this next one. If I look at the limit as x goes to a of x, what is it? A. Another way you can ask this question is, as x gets close to a, what does x get close to? A. See? See how easy that is? Oh. Okay, so we can have that. So now suppose we have two functions. F of x is getting close to L. G of x is getting close to M. So if f is getting close to L and g is getting close to M, what's happening to f times g? It's getting close to L times M. What about the following? Okay, so again, f is getting close to L, g is getting close to M. What about f divided by g? What's that going to get close to? L over M, unless, what's our worry? Yeah, unless m equals 0. Now what happens if m equals 0? Well, it depends. If L equals 0, it means more work. More work. 0 over 0 is more work. And if L is not 0, divided by 0, it means not going to happen, right? Well, we'll talk more about it next week, I think. Okay, so now, how about this one? Again, f is getting close to L, g is getting close to M. And I'm looking at some constant c times f plus some constant d times g. This is called a linear combination. Well, what do you think happens? Yeah, c times L and d times M. So in other words, it works well over addition. It works well pulling out constants. The last one is kind of a strange expression, but if I have f of x to a power, then what happens is this goes to L to the power. You know, as long as it makes sense. There are some weird scenarios where it's like, that expression doesn't make sense. I'm not going to define what that means. But one of our other big takeaways, and this will be sort of a huge theme in Calc 2, is that limits work really nicely with polynomials. because it works very nicely with x, so it works very nicely with powers of x. It works very nicely with constants. It works very nicely with combining constants and powers of x's together. And that's what polynomials are. So polynomials will put us in our happy place. And this is going to become more and more true. By the time we hit the end of Calc 2, we're going to be like, I love polynomials. Oh, they're the bestest. Polynomials. They're awesome. All right. So the punchline is, limits do what you think they should do. So don't be like, limits are hard. It's like, no, limits tell us what should happen. So what should happen? And then we figure it out. Okay, so let's do an example of where we're going. So I have a function, f of x is 2x squared minus 3x, and we want to find the average rate of change from 1 to 1 plus h. Simplify as much as possible, question mark? No, that's not a question. We're going to turn that into an exclamation mark. There we go. Yes, we're definitely going to simplify as much as possible. So don't worry, this is one we'll do together. Okay, so first off, is there an average rate of change formula? Right, so f of 1 plus h, subtract f of 1 over 1 plus h, subtract 1. F of b minus a over b minus a. So this is f of 1 plus h, subtract f of 1. 1 plus h, subtract 1, also known as h. Okay. And just for emphasis, this is our average rate of change. Now, the moment of truth. What is f of 1 plus h? So let's remember, we have f of x is 2x squared minus 3x. So what's f of 1? We'll need that in a second. 2 times 1 squared minus 3 times 1, right? And then that's 2 minus 3, which is negative 1. All right, let's say f of 0. 2 times 0 squared minus 3 times 0, which is 0. Okay, that was pretty easy. What about f of t? What is that? Two t squared minus 3 times t. Okay, what about f of a cat? What is that? 2 times cat squared minus 3 times cat, right? Now you're probably thinking, but what is that? Well, it's nonsense here, but we have a rule. No matter what we plug in, we apply the rule. Okay. So what is f of 1 plus h? What do? You put 1 plus h everywhere there's an x, and that's, we don't do anything fancy, just everywhere where there is an x, you put a 1 plus h. And by the way, parentheses are friends. We like parentheses. Some of our best friends are parentheses. They help us keep points. And this step right here, plug in f of 1 plus h, a lot of students have lost points, but not us. We're not going to let them take any points from us. All right. Can we expand 1 plus h squared? 1 plus 2h plus h squared. Then we can distribute through this, so we get 2 plus 4h plus 2h squared minus 3 minus 3h. Now that's why parentheses are important, to help us remember to distribute all the way through to all the terms. Now if we gather, hunter-gatherers. Well, we have an h squared term. What about for h? What do we have? You have h, because you have 4h minus 3h is plus h. What about our constant terms? Minus 1. Okay, so plugging in f of 1 plus h, that's an important step. Okay, so getting back to our computation. We know what f of 1 plus h is. We just did that. So that's 2h squared plus h minus 1. We also know what f of 1 is. It's minus 1. And we're dividing by h. Okay. Does anything happen? The minus 1s cancel. Oh, well that's nice. So we currently have 2h squared plus h over h. Now remember, we're supposed to simplify as much as possible. Has this been simplified as much as possible? Well, what can we do to simplify even more? Pull out an h. Okay, so h times 2h plus 1 over h. The h's cancel. Now, this is important. We'll talk about why it's important in a second. So what do we have? 2h plus 1. Can we simplify that any further? No. So this is the first part. What is the average rate of change between 1 and 1 plus h? And now, we're going to do the following. We have the limit, as h goes to 0, f of 1 plus h minus f of 1 over h. Now, notice if you plugged in h equals 0, you would get f of 1 minus f of 1 over 0, which is 0 over 0, which means it's more work. But the good news is it's work we've done. Now, what's the idea? This we already mentioned is the average rate of change. And the idea is I'm looking at the average rate of change of points as they move closer together. Well, in terms of your secant line, you have a secant line, but if your points are really close, what do you look like? You look like the tangent line. So what happens is this inside part is your average rate of change, but the limit, this is your instantaneous rate of change. So this is actually computing an instantaneous rate of change of the function at 1. Well, we know from what we just did that we can replace this expression by 2h plus 1. Okay, now, what happens to 2h plus 1 as h goes to 0? When in doubt, plug it in. You plug it in and ask, do I need to do more work or do I not need to do more work? You might say, how do I know if I need to do more work? Is it 0 over 0 or not? Okay, plug in 0. What do you get? So what's the answer? It's 1. So we've now done an instantaneous rate of change. Woohoo! And it's only our second lecture. Wow. We are flying. Yes? Okay. All right. Now, I will point out, as I said, this, if you plugged in h equals 0, you would have gone a 0 over 0. How did we not encounter a 0 over 0 here? Well, the punchline is we canceled. This cancellation was essentially canceling out the zeros of the 0 over 0. All right. So now, a problem. And this one's going to be all you. Let f of x equal x squared plus 3x minus 10 over x minus 2 if x is not 2, and 1 if x equals 2. There's two questions. What is f of 2? What is the limit as x approaches 2 of f of x? Does somebody have an answer to the question, what is f of 2? 1. How do we know it? Because it tells it. Now, that's a pretty good clue. How do you find the limit as x approaches 2? Does anyone have that? 7. 7. Now you might notice if you plug 2 into this expression upstairs, 4 plus 6 minus 10, 0. 2 minus 2 is 0. It's 0 over 0. That's why we can't just say, oh, for all x it's that expression, because it's not defined for x equals 2. Now the question is, did they define it well? No. Okay, so what's going on? So if I were looking at the limit as x goes to 2 of f of x, well, now when I talk about limits, I say what's happening nearby, but I ignore the information at 2. So I'm ignoring what happens at 2. I'm just saying what's happening near 2. Near 2, my function looks like this expression, that polynomial over that polynomial. I see 0 over 0. When I see 0 over 0, I'm thinking cancel out the zeros. So I'm looking for ways to get cancellation. Now with polynomials, that usually means factoring. So one of the things you're going to do a lot of is factoring. Expand polynomials, factor polynomials. We'll talk about other algebra things. You might be doing things like adding fractions. You might do things like multiplying by conjugates. All these wonderful things. But the punchline is we can factor the numerator. The x minus 2's cancel. And it's okay for us to cancel because we're canceling x minus 2 terms and they're non-zero. Canceling zeros are dangerous. You shouldn't cancel zeros, but you can cancel non-zeros. We say, aha, it's really x plus 5. And so x plus 5, no surprises. You plug 2 in and you get 7. All right. So there we go. There we go. Okay, a few other things we can look at. Suppose we have the following function. G of x is sine 1 over x if x is non-zero, and it's 0 if x equals 0. This one we'll do together. G of 0 is what? It's 0. But now, what is sine of 1 over x? Well, we know what sine of x looks like. And what it's doing is it's oscillating. It goes up and down. So you say, okay, well, what is sine of 1 over x doing? Well, the thing is, what's happening to 1 over x as x is getting close to 0? So again, don't worry about the sine of 1 over x. Just what's happening to 1 over x as x gets close to 0. There's an asymptote involved. Good. So what's happening to 1 over x? When you say it's an asymptote, what kind of asymptote? Vertical. So it's blowing up. It's getting huge. And it's getting huge very, very quickly. So what effect does that have? Well, the effect that it has is now, instead of trying to put these infinitely many oscillations over a very long time period, what it does is it says, oh, I'm going to compress it all to that. So I'm going to try to go up and down infinitely often near 0. And of course you can say, well, what about the other side? And the answer is very similar. It looks like that. So as you're getting close to 0, what value is sine 1 over x approaching? Or is it even approaching any value? What am I getting close to? Am I getting close to 0? I mean, I get close to 0 infinitely often, but do I stay close to 0? No, I get close to 1 infinitely often, but do I stay close to 1? No. What am I doing? Am I getting close to any one single number? No. This is an example of a limit that does not exist. So there's no single number which works. So it is possible for limits to not exist. And it's not just because necessarily of a division by 0 problem. It's because it's not settling into one particular number. So this is just a case of, hey, things can go wrong. Yes. Yes, they can. All right. Well, we're just going to go through a bunch of examples here. Hopefully we'll get good at doing some of these. Find the limit as y approaches 3 of the square root of y plus 1 minus 2 over the square root of y plus 6 minus 3. Okay. Cool. 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 Now, when in doubt, what do you think the first thing you should check is? You should just plug it in. Your first instinct should be like, let me plug it in. And let's see what's happening. Okay, so we plug it in. All right, what are we getting upstairs? Square root of 4 minus 2, which, yep, that's 0. Okay, what are we getting downstairs? Square root of 9 minus 3, which is 0. And 0 over 0 is? More work. More work. It's not 0. It's not 1. It's more. More. Okay. Well, now we know we're in our more work phase. Cool. So, mindset. We want to get cancellation. And when we see algebraic expressions, in this case we're saying as y goes to 3, we say, you know what we should try to cancel? We should try to cancel some y minus 3s. We should look for y minus 3s that are somewhere here, one on the top and one on the bottom, cancel them out. Life is good. Bob's your uncle. Doesn't look like there's a y minus 3 there. Okay. But that's all right, because we've done algebra. We've been down that road. So we're going to apply our wonderful algebra knowledge. Okay. So algebra is going to say, what are some things we can do? And in particular, what don't we like? We don't like the square roots. Is there a way to get rid of the square roots? Well, squaring is not what we want to do. I know that sounds like a really cool thing, like, oh yeah, square root. But no, we have to remember, we can only do things to our expression which doesn't change it. Squaring changes things. Now you might say, well, okay, what are things then we can do? Well, the answer is you can add 0 however you like. And you can multiply by 1 however you like. But not just any one. We must choose. And choose wisely. For a well-chosen one will get us closer to the answer. So, anybody have a candidate for a well-chosen one?
Square root y plus 6 minus 3?
Square root of y plus 6 plus 3. Aha! Someone has suggested. The conjugation. Our conjugates. So, if you see a square root symbol showing up inside of a limit expression, think conjugates. Now, how does it work? If you have a minus b somewhere, let's say it's downstairs, then multiply by a plus b. Now, I have to make sure I don't change it. So I'm going to multiply both top and bottom. And what will happen is I still have the stuff I had before on the top with a plus b, but what's downstairs? Well, it's a squared minus b squared. So it's the difference of squares. Now you might say, well, wait, what about the plus ab? Well, there is a plus ab. What else is there? Minus ab. So they cancel out. So that's why the conjugate is you're like, ooh, I'm going to change this minus into a plus. And by doing that, you square things. Now, people said, let's square things. Well, yeah, we do it, but the way we do it, we have to do it in a way that's legal. So this helps us get there. Okay, so we have some terms upstairs. We're right now, we're not in the limit, we're just working on algebra. Let's start with the upstairs. What do we want to multiply by upstairs? Square root of y plus 1 plus 2. Now, I'm going to have to put that downstairs as well. That way the net effect is I've multiplied by 1. Now you might say, huh, that's a really curious thing you've just done, Steve. Why did you do that? Well, I anticipate I'm going to have to do work downstairs. This is a twofer. 2 problems for the price of 1. Wow, what a bargain. What do I want to multiply by downstairs? Square root of y plus 6 plus 3. Square root of y plus 6 plus 3. Again, I'm multiplying by 1. This all becomes 1. But it's a well-chosen one. Now, there's some advice. We want to multiply stuff out. But we don't want to multiply stuff out if it's not going to help us. So only multiply stuff out that will help you. If it doesn't help you, don't multiply it out. Okay, so in our case, that's why I was careful. We're going to multiply the first pair of terms on the top with the first pair of terms on the bottom. Okay, so what happens? We get, on the first, multiplying these first terms together, what do you get? So this is a minus b, a plus b. We end up with y plus 1 minus 4 times this other stuff. Downstairs, what do we get? Y plus 6 minus 9. And then this other stuff. Okay, y plus 1 minus 4, also known as y minus 3. Y plus 6 minus 9, also known as? So what happens to those terms? They cancel. This is the more work we talked about. The more work is getting to a point where you get cancellation. Nice. So what's the whole punchline of this? The punchline is we've now shown that this expression here on the inside is the same as this expression. So our limit, we can now say, is the following. It's the same as the limit as square root of y plus 6 plus 3 over the square root of y plus 1 plus 2. Well, now what should we do? Plug it in. What do we get? What's upstairs? Square root of 9 plus 3, right? Now the good news is, game over, man. Game over. It's not 0. When it's not 0, it's game over. Okay, what do you get downstairs? Square root of 4 plus 2. Okay, square root of 9 plus 3 is 3. 3 plus 3. Okay, you get 6 upstairs, 4 downstairs, 3 halves. Okay. A quick example here, and then we'll throw out the multiple choice. You can do stuff with trig, too. We're going to do a lot of stuff with trig next time. Trig is going to be a big theme of our next lecture, but limit as theta goes to 0 of sine squared theta 1 minus cosine theta. When you plug in 0, what happens upstairs? You get 0. What happens downstairs? 0, which is more work. Okay, but what can you do? Well, what's another way to say sine squared? 1 minus cosine squared. Can you factor 1 minus cosine squared? 1 minus cosine, 1 plus cosine. It's a difference of squares. And then what can you do? Cancel. That's the more work. It's getting that cancellation. So you say, really, a better way to think about this limit is its limit of 1 plus cosine. Well, what is this? It's 2. Because you plug in. Theta equals 0. 1 plus cosine of 0 is 1 plus 1. 2. All right, we only have like a minute. I'm going to throw out the multiple choice. And I know you can't do this in a minute. But I want you to think about what would be your first step. What's the very first step? Or what are some steps you would take? All right, our time is basically up. Does anybody want to take a wild stab in the dark? E is a great answer because it's right. Wow, we should do multiple choice more often. Okay, so what are some first things? Check, are you getting 0 over 0? Factor the upstairs. Rearrange the denominator. Oftentimes, you have to think about, how do I rearrange? The nice thing about the plus minus is it allows us to combine things, it allows us to split things, it allows us to rearrange things. But these are all algebra things that you can do. It might take practice, but you can do all of these steps. All right, that's it for today.